Welcome back. So in the last module, you saw different types of robots. You were introduced to robots, its anatomy, right? You saw different aspects of the robot that make actually a robot. So what is it made up of? It is made up of actuators, it is made up of links, it is made up of different sensors and effector grippers and so on and so forth. So you now know different things that make up a robot, and you also know how a robot is classified, how technically a robot is specified by its data sheet by the manufacturers. So one thing that was very common in all of them was actuators. Why? When you saw a robot is made, that actuator is something that makes a mechanical robot move, So that is what. So even to classify the industrial robot, you require whether it is driven by an electrical actuator or a hydraulic actuator or a pneumatic actuator. So that helped us in classifying the robot. Even while specifying the robot, how much is the speed by which your joint can go, how much is the end effector velocity a robot can achieve. These all things depends on the kind of actuator you have to make that robot. Okay, so yes, that is why actuator has come up as a significant thing that makes up a robot that we should discuss. Okay, in the last lecture I discussed something about industrial electronic hardwares which is there in this type of robots. Communication interfaces, you now know how to communicate with these drivers, different sensors which are attached, right? So once you are done with your calculations, you want now your angles to go to the joints. Yes, how that will go? That will go using the communication interfaces to the drivers. Okay, industrial PC, different systems, you now know. Okay, in today's lecture, we'll discuss about actuators. Yes, actuators are the key to success. This is the tagline that I have been telling to my students since long time. You know why? Because the company that you see are developing in robotics, they are good in actuators also. Okay, we are able to make a good EV if we are able to make a good actuators for its wheels, right? So same in case of robotics, you are able to control the joint precisely using these actuators, then you can make very good robots, right? The precision of the robot, the capability of the robot is defined by the type of actuator it has, right? So a company which has accessibility to these kind of actuators at competitive cost are the companies who are successful in making these kind of robot, right? So engineer is capable if he is able to control these kinds of actuators. Okay, so that is very important aspect of any engineering as such, but yes, in case of robots also it is very important. So in this particular module we'll be discussing about actuators. So yes, coming to this, so yes, I'll be introducing you to different kinds of actuators, right? Why electric actuator only, why not hydraulic, why not pneumatic? We'll discuss on them. DC motor as such I'll be discussing in today's lecture, right? And what is difference between motor and actuator, and what are drives that actually drives these kind of robots. So DC motor and its drives will be discussing today, and introduction to different kinds of controller drive systems will be doing, that is specific to DC motor control in this lecture. And I'll also be demonstrating DC motor using industrial system. Okay, so here we go. So yes, actuator is a component of a machine that is responsible for moving and controlling a mechanism or a system. For robot, it actually actuates the joint. So you got it. So it is a joint which is actuated by the a kind of actuator it has. Okay, actuator normally has accessories. It has limit switches. Let us say if my joint goes beyond certain angle, I have to stop. So it includes sometimes software limits or a physical limit switches to stop it once it reaches there. It also has gear boxes so that it can elevate the motor's torque to a given scenario. Let's say if my to handle the load capabilities of my robot, let's say okay, more torque at one of its joints. So yes, That actuator may have a gearbox to enhance the torque capability of the motor which goes there. It has some feedback devices to get the precise angle values wherever it is. It requires a controller. Normally a motor can run just by providing electricity, whereas an actuator needs a controller because it has to travel through a path maybe. Okay, it has to follow a trajectory while moving through its joint, right? And a source of energy, for example, electric actuator, hydraulic actuator, pneumatic actuator, or maybe heat is required, so kind of energy is required. Okay, so the displacement is commonly linear or rotational. So actuator can be both. It can be a linear actuator, it can be a rotational actuator. So different types of actuators are there. It can be electric or a fluid powered like hydraulic or pneumatic, thermal or magnetic, shape memory alloys, photopolymers, piezoelectric devices are also there to move your joints. Okay, so with all these kinds of actuator, not all motors are actuator. You know, motors are normally a sub part of an actuator which is residing inside the actuator, right? So motor along with its accessories like limit switches, gearbox, feedback devices and all is called as an actuator. So now you know the difference here. So yes, why electric motors are actuators? Why? Because there are other options we have, that is hydraulic or pneumatic actuators. So what is the problem with that? Okay, so yes, because in case of electrical actuator, you see your electricity is available all around, right? At your home, at industry, right? It can be even generated somewhere on the spacecraft, right? Using solar energy. Okay, using tidal energy you can generate at the sea also. So yes, you can generate electricity all around, like it can be made portable also. If it is stored in form of batteries, you can store it in form of battery, then it can be used on a moving aero vehicles or maybe on a ship somewhere or a underwater vehicle, right? So it is widespread available, right? It is lighter, it is very, very light because the source remains somewhere else. Hydro power plant or a thermal power station is situated quite far apart. You are getting this electricity by the wires that comes to your home. Finally, you are not generating that noise all around. So it is very, very lighter, it is quieter, it is cleaner at the site. At the site, thermal power station do generate smoke and all, but that is there at the power plant, not at the site. Okay. So yes, it has a very high conversion efficiency. If you talk as compared to pneumatic or hydraulic, so you don't waste energy. Quite a lot of it is actually converted to the power that you see at its shaft. Okay, so no pollution in the environment, working environment where you are there, right? And it has a better accuracy and repeatability. We will talk about these terms very much in detail. Repeatability we have already talked about a bit while defining industrial robot specification. Accuracy and repeatability will be defining very much when we will be defining a few other parameters of the robot in later modules. So yes, it is easy to maintain and repair. You see electrical motors are nowadays repaired next to your home maybe. People are there who are repairing your electric fan, your electric motor, washing machine motor or whatever. So yes, it is trained people are around to repair that also, right? A drive system is well suited to be controlled electronically. You mean electricity is to be controlled by electricity. So there is no transformation in between, right? So you have some controller that generates 0 to 5 volt of current to control, let's say, current in your motor that varies from 0 to 10 ampere. So you just need a power amplifier in between. So that transformation is very, very easy. Okay. So yes, apart from this, it has some drawbacks also. Yes, it has some electric shock and fire hazard. If it is in an environment, let's say you are inside a mine where mass gas is there, so what will happen? Even a simple spark can cause huge amount of explosion, right? So yes, it has to be shielded to take care of. Yes, electric shock, yes, you by proper safety and all, it can be taken care of. It may cause overheating on long runs. Most of the robots that you see at the rear part of it in the motor, you sometimes see these symbols which are here. So one of them belongs to and this is for the electric shock hazard, and other one is for heat, that is the temperature hazard. It may be very hot, so those are the warning symbols which is posted at the rear part of your actuators which are placed in the robots. So yes, these are some of them. Yes, you have to take care and then it is fine, that's all. And then let us come to PMDC motor or actuator, that is permanent magnet DC motor. We'll talk about motor. Actuators are, along with the motor, all the accessories comprised to make it a actuator. So we'll now call it as a motor, no issue with that. So yes, principle of operation is very old and you already probably know it. So it is the conductor of the armature will experience a force. If it is a conductor, it carries a current, right? It is placed in a field, it is placed in a magnetic field that crosses this, right? So this conductor is placed in a field and then it will experience a force which is mutually perpendicular to the field and the current, right? So that is what is given by Fleming's left hand rule, that you probably know through your high school physics also. So yes, this conductor or the armature will experience the force if an electric current in that conductor flows at right angles to the magnetic field. Okay, so basic components that this motor includes is armature. Armature, you see, it has a good amount of conductors. These are all coils. Okay, these are conductors. Conductors are within these slots. It goes within these slots. So they are longitudinal conductors. Okay, so this is a rotating armature. This will rotate like this or maybe otherwise. Okay, so it also has, let's say this is known as a commutator. Commutator, that is to transfer current by having some sort of contact over here. This will transfer current from here to the conductors. Okay, so that is what is an armature, and this is mounted on top of bearing supports so that it rotates about its axis. It is supported by two bearings at its end and it can rotate. So that is what is known as an armature, that is the moving part of a motor. And then it has a stator. Stator has some permanent magnets, or maybe these magnets are electromagnets which are there to produce the magnetic field. So you have a magnet here, you have a magnet here, two opposite magnet will finally create a magnetic field like this. Okay, so you will see a magnetic field that goes like this. Okay, so finally once you place this armature here, you see over here, so this will be the direction of your field and these are the direction of your current carrying conductors. Okay, okay, so now you got the picture how it is going to place Fleming's left hand rule and create some sort of torque. You will see it very much in detail now. So yes, it also has brushes and commutator to pass on this. As I have showed you here, these are the commutators. Now you have some sort of brushes which continuously keeps in contact with these sort of commutator, so that current can be passed on from the brushes to these copper thing, and finally it will go to the coil and come out. Right, it goes from here, it comes out from here, or it may be otherwise. Okay, so yes, this is there. So each carbon brush is spring loaded. They are placed in the slots over here. Okay, so as it wears out, it comes closer. Finally, when it is worn out totally, you can simply replace this with a new one. Okay, so yes, they continuously keep on swiping across the commutator. Rotating commutator, you have continuous contact so that it rotates and this keeps on slipping. So yes, this is something which may cause a spark, and later on it requires some sort of maintenance also. Forget about that, let us first learn the principle of operation. So yes, this is to supply the current to the armature coils. Okay, so now here it is. So all the things are now mounted here. Now you see the complete picture of this. One of the pole is shown here. So you have a pole which is here, which is north pole, and you have another pole which is here, this is south pole. Finally this is going to create some sort of magnetic field like this. Okay, let me draw it with different color maybe. Okay, so magnetic field as I have drawn earlier, so it goes like this, it goes like this. Okay, so your coil is now placed inside this. Okay, so now you have conductors, they will carry the current, so they are like this, they are like this. Okay, so once it is here, so you see you have now the commutator which are here, okay, so that will transfer the current from here to the carbon brushes, and finally these are the points. From here it goes to the conductor, which are now orthogonal to the field. So if you are somewhere in the cleaner space, yes, so this is the conductor, this is your field. So finally if this is your field, this is your conductor. Okay, so finally you will see a cross product of these two. Finally it will give you a force which is perpendicular to both of them. This force will now create a torque. So how? Let us see. Okay, going to this picture, yes, this has an isolated picture of one of the conductor which carries the current. See how it is done. So yes, so now I'll draw this once again. So yes, you have a field is shown in a blue over here. This is the field direction, that is the blue color, that is the field direction, and these conductors, they carry current. So it is shown as a green color here, so it carries current, it comes back like this, finally it is out. So you see your current is like this, you have a field which is like this. Okay, finally this is creating some sort of magnetic force. So this is the force that you see at this end of it, where current flows in opposite direction. Okay, here the current flows in different direction, and you have a field which creates a force in this direction. Ultimately this creates a couple which can rotate this shaft, somewhere like this. Okay, so yes, this is how it works. Let us say you have now let us see the parameters, let us analyze the physics of it more clearly. Okay, so yes, what is the magnetic moment here? If you remember your high school physics, magnetic moment is given like this. It is nothing but a current into the area vector. Area vector is nothing but, if at all you see a area which is inclined like this, okay, this is your axis. So perpendicular to the plane of this area, you have a normal, that comes out of it. So that is your area vector. So that is the vector which is perpendicular. So area vector is the magnitude of this area into the vector which is here. So that is what is your A. Okay, and then so that is Ia into A, that is the magnetic moment. Ia is the current through the conductor. Okay, and area is given over here as, because there is a bunch of coil. If you saw that actual armature carefully, it has not just one wire at particular place. So you may have a bunch of wire that makes n number of conductor which is taking this current from this loop, okay, through this loop. So this is n over here. 2r is the radius. If this is the radius, okay, so it is r and it has another r, so r. So that is the dimension. This is your L, that is length of this conductor. So 2RL effectively gives you the area which is here. So n times those area, because you have multiple turns of this wire, so n times that area. Finally this is A and N. A is the number of all those area, number of times added together finally gives you the total area. It is not just one winding, it has multiple windings. So this gives you the direction. So magnitude is A, whereas a small n vector is a unit vector which is orthogonal to this area vector. Okay, so yes, moving ahead. So yes, number of turns of the coil, and r is the radius of the rotor, L is the length of that conductor. So effectively N is the unit vector which is perpendicular to the plane of the coil. So yes, rotor torque is given by magnetic moment cross product to field, that is B. Okay, so effectively you will see M into B sine sigma. What is sigma here? Sigma is the angle between M and B, because it is a cross product. So effectively you will get Km Ia sigma. What is Km? I'll tell you. So B is the constant magnetic flux which is there, because these magnets are permanent electromagnet. Even if it is an electromagnet, doesn't matter, the current is always constant through the exciter coils. That makes that electromagnet a constant one. Okay, a constant magnetic flux one. So field remains constant. Okay, so yes, sigma is the angle between B and A. So yes, so finally you got torque is equal to Km Ia sine sigma. So now to make, so you see this torque is not a uniform one. It depends on the angle. As the rotor rotates, torque is a variable. It becomes 0 degree. It becomes 0 degree. In that case, you see a zero torque. So how it will cross? Maybe through inertia it will cross. Can it start from that position? No. So in that case, what you do, you don't just have one single conductor, you have multiple conductors. Now look at your armature once again. Okay, so let us see the armature once again. So how was this? It has multiple commutator and multiple conductors. So if one of them crosses that field, another one enters, another one enters, another one enters. So one of them is always getting into the field, other one comes out of the field. Okay, so effectively what you see is a constant torque that is there. So one of the sigma becomes 0, other sigma is entering, leaving, and it is entering and it becomes 90 degree. Okay, so you see almost by increasing the number of poles, you can always make this torque almost a constant. So effectively what you see is tau is equal to Km into Ia. So sigma no more is a variable. If you sum the torque, sum of the torques of all those coils which are there, so effectively that annul the effect of sigma. Okay, so it becomes almost negligible pulsation in torque. So almost constant torque you will see. Combined over the motor inertia, rotor inertia, almost that is not seen even as a mechanical vibration. Okay, so this is what. So a standard equation for any motor, not just a DC motor. This is the basic principle of any motor. It can be a servo motor, it can be a stepper motor, it can be anything. So this is the torque which is created out of a conductor which is carrying a current and it is lying in the field. Okay, so this is the torque which is given, and each type of motor, any type of motor has multiple number of poles. So you see similar equation is there even for servo motors or any kind of motor. So yes, this is a general equation of motor. Okay. So now Km is equal to N times B into A. This is just derived out of what the variables you have. Okay, that is the motor constant. It is known as motor constant. Okay, if it is tau by Ia, so unit is Newton meter by current. Okay, that is ampere. Okay, so what is this? This is basically a relationship between speed and the torque characteristics of a multipole DC motor, that is PM DC motor, right? So you see tau is equal to Km into Ia. You can very well notice here that torque is proportional to the current which flows through the armature coil. Okay, so that is always there. So if you can relate one of the very standard equation that says torque into omega is power of a shaft. So what is this? As because a constant amount of power is fed into this system, so if torque increases, angular velocity should decrease. But yes, it should not be in a straight line. So what you see here, this is a plot between the torque and the rotary speed, torque and the rotary speeds, and it is in a somewhere like this. Actually it is not like this. Actual relation is something else. This is the operational diagram of a typical motor, DC motor. Okay, so I'll show you the correct picture of this also. So yes, so higher the applied EMF, that is the voltage, higher is the speed. So in order to control the speed of a DC motor, you have to apply more voltage to it. So effective voltage should increase. So higher is the current, you can increase the torque. So both of them can be controlled. So higher is the torque, that means higher current is flowing through your conductor. Reversing the polarity changes the direction. So you see, as a basic principle, if a conductor is carrying current in this direction, if it sees force like this, if you reverse the polarity, it will see the force which is opposite to it. It is quite easy to understand. So this is what is creating a negative couple, and finally the negative direction of rotation. Okay, so this DC motor is very well controllable for speed, the torque, and changes it and the direction also. Position can be controlled if you have a feedback mechanism that checks the position every time wherever you are, and then you can create a closed loop and you can control. That is known as a servo. We'll talk about that also. Okay, so how does it look like this type? So you see, there are few parameters to notice here itself. So this is the stall torque. This is the position which is known as stall torque. This is the condition when you completely stop your motor from rotating. This is the maximum torque which is delivered by the motor when it is completely stalled. Okay, and this is the no load speed when torque, effective torque, apart from the torque which is there due to friction and all. So if it is not loaded, this is the maximum rotational speed that you can see. Okay, so you have to have run your motor somewhere in between. This is the continuous operation range. Okay, so that is where you should be. So higher is the voltage, higher is the speed also. So every speed line will have a different characteristics curve. Okay, so if at all you increase the voltage, speed also increases. So you will see a different line. You will see a different line. Another line may be something like this. So that also creates different lines. Okay, so we'll see all these details very much closely in the actual picture that is on the data sheet now. Okay, so this is a standard data sheet of a motor, you see. So it says very good amount of parameter that will let you select a particular kind of motor for your application. Okay, so yes, this is nominal voltage, no load speed. So this is the speed we are talking about, that is no load speed. When it is, this is the stall torque, this is the stall torque. Speed to torque gradient, that is the slope of this line that you saw. No load current that is flowing through this motor. Maximum power output, this continuous torque is the continuous operation region that I showed in green color. Okay, so maximum permissible speed, if it goes beyond that, it is dangerous and you can break your robot, break your joints, maybe your motor over here. Thermal resistance, that is in ohms. So these are all helpful in designing the controller for your joint. Okay, that is the joint. So thermal resistance will be useful. Thermal terminal inductance will be useful. Right, we'll talk about this. Motor inertia, that is the armature inertia, that also is a mechanical value which will be very useful. Torque constant. This is what is your Km, that is the motor constant you just derived. Okay, so these are some of the parameters which are there. Not all manufacturer will give you this many details because probably they haven't tested their motor to this extent. Okay, so this is the actual curve, how it looks like, and you see, I'll just zoom it out so as to make it clearly visible. So yes, it has different motors of different parameters over here. So this is the operational region, recommended operating range, and for continuous operating you should be somewhere within this area over here. Okay, and this is short term operation. Yes, you can go here also if it is for short term operation. Okay, so this is very useful information. So intermittent operation, like in case of robot also, you can be very safe over here also. So let us look closely. These are the dimensions. So tabular wise, any of the motor kind, is over here. You can simply group one of them. Let's say this motor only, it has all the parameters that is defined earlier is here. So these will help you to select different robots. So maximum torque that it can deliver, stall torque, right, and continuous operation torque is also there. Continuous, you should not go beyond, it is in millinewton meter. This is for a small motor. Even for big industrial motor also it will be something like this. Okay, so thermal resistance is there, that we will be using later on. Maximum continuous current, so this is the continuous current. This will help you to select a suitable driver to drive this kind of motor. If it is 500 milliamp, 0.5 ampere driver should be good enough. So yes, its starting current is a intermittent current, not intermittent, starting current only. So that you will see it is very high, 3.2 ampere it is going to draw while it is starting. So starting should not take too much time, otherwise your driver may go bad. So just check the specification of your driver also. No load current, this is even without it is running freely, it is carrying this much of current. So yes, so this is all the parameter that is very important, that you should look for when you select your robot for a particular application. Okay, so yes, this is a typical data sheet that I have shown, that shows the characteristics of a multipole DC motor. So you see, so yes, DC motor can be also of various kinds. So just now you saw a permanent magnet over there. If that is not a permanent magnet, what it is? It has a field coils. So field coil also will draw electricity from the source, right? So once the current comes, it may be divided to field as well as to this. So if field coil and the motor armature is connected parallel to each other, that is known as a shunt DC motor. So armature winding and the field windings are connected in parallel. Speed controllability is good as back EMF is proportional to the applied voltage at a steady state. At a steady state, speed controllability is very good. Okay, so this is a type of motor. And then you have a series type of motor where field coil and the armature is drawing same amount of current, same current flows through the field as well as to the armature. So now you know, so starting current will be very high to the field. So field windings are, a large current flows through both the winding at least while starting. So it will have a very high starting torque. So speed controllability however is very poor. Okay, so once the rotor takes up the speed, so it takes up a small amount of current, right? So if it is no load, so it can draw a less current. So yes, this type of characteristics is also useful. Let us say you want to have a starting motor of your car, maybe starting current is required to be very high, but in that case normally PM DC motor is there. So anyway, so that is there. And in case of compound DC motor, a part of the coil is connected in series whereas other one is connected in a parallel way. So it has a joint characteristics of both series and shunt wound motor. So these individually may be suitable for not just for robots, maybe for other automatic equipments which are around, maybe for a conveyor, maybe for a rotary table and other parameters, other equipments which are around, right? So yes. So yes, now what you saw with the DC permanent magnet DC motor, it is referred to as torque motor because it can provide you with a very high torque. That is the reason it is used as a starter of a scooter, right? That is a IC engine driven scooter, right? And then you have magnets should have a very high flux density. Your PMDC motors, your magnets, normally a no medium magnet, which are having a very powerful field, which can create very powerful field. No field coils are used in case of PMDC motor. Okay, yes, they are very advantageous in a way. Excitation power supplies for the field coils are not required, so it doesn't draw your energy over there, right? Reliability is improved as there is no field coil, less number of parts, so that cannot go wrong. So that is permanently there. right? And power loss from the field coils means efficiency and cooling are improved, right? So yes, it doesn't need further cooling of the field coils also. But yes, DC motors has brushes. As you know, it is continuously in friction and that wear will occur, and over the time it needs some sort of maintenance, so that cost will go high, but still it can provide very good amount of torque. That is the takeaway of this kind of motor. Okay. So now how to drive this motor. Okay. So let us first introduce you to a transistor switch. Hopefully you know this with your basic electronics course if you had any, right? So this is a typical transistor which is biased in a way using these two resistances, and it is connected. Okay. So if it is in a switching mode, not in an amplification zone, it has already saturated. In that case, it is just about to saturate it by even a small amount of current if it is fed from here. So if you apply a small amount of current from here, it will get biased and it goes from here to this. Okay, and current flows. Okay, so that is the gate type of operation, right? So if you don't apply current from here, so if no current is there from here, so current will not flow through this transistor, and finally it will go all from this direction. So it is just like a NOT gate. If you provide 1 over here, you see 0 over here. So if you provide 0, if you provide 0 here, you see 1 here. If you provide 1 here, you see 0 here. So this is just a NOT gate operation. Anyway, I am not here to talk about NOT gate operation, but yes, this is very, very helpful in making your load connected like this. So it becomes very much like a switch. You can connect your motor like this. So if you have a transistor, right? So you can connect your, so this is your supply, this is your controlling current which is here. So if your motor is here, right? So as soon as you provide current to this line, so transistor is now working. Okay, so now the current comes to the motor and motor starts running. So a small amount of current can now control huge amount of current from here. So this is just a switching operation, how it is useful. But there is another way of running it also, this kind of motor. This time what I will do, I will connect this transistor to the ground. Okay, and this time I have fitted this motor over here. Okay. So now what will happen, as soon as I provide 0 over here, that is connect this to the ground, what will happen, all the current from here will flow through the motor and motor will start. So 0 to run the motor. If you provide 1, that is logic value 1, that is the control signal is here. So in that case transistor opens up and current flows from here to the ground. In that case motor is off. This is another way of connecting it. So these are the two methods how to control DC motor using a standard transistor. So yes, but then there are another way of controlling this also. You can, instead of using a transistor as a switch, you can also use MOSFET, that is the metal oxide silicon field effect transistor, FET switches, which are faster in response, and they also can carry huge amount of current as compared to a transistor. Okay, a normal transistor, right? So yes, moving ahead. So now if you see standard H bridge drivers, they are used to control DC motor. How? Let us just look at very, very carefully. This has a capability to change the direction of your current that is flowing through the motor, right? As well as you can switch on and off your circuit closely. Okay, so let us just look. So now in this case what is happening? Okay, so this switch is closed, that is enable switch is closed. Okay, so whatever potential you are applying over here, it creates a current. This switch is closed. From here it goes to this, because these two switches were closed, these two are open. Okay, finally the current will go back. So this is how this is making current flow in this direction. Okay, but what is happening over here in this one? you have closed this one, this is closed, this is closed, this is open, this is open. In this case, you have current that flows like this. Okay, finally it goes back. So in this case, you have current that flows like this. So you see, you can very well reverse the polarity that is across the motor terminals. Okay, in this way you can clearly change the rotation direction immediately using H-bridge. Now how to control the speed of your DC motor. In this case, what you can do, you can use a S-enable switch. S-enable switch, this uses PWM for controlling the power that is fed to the driver. Okay, you know, if you can reduce the voltage of across your terminals, that can reduce the speed of your motor. But yes, that has a problem. Maybe at a very small amount of voltage, motor is not running and current keeps on flowing through your coil. So if it stays there for a longer period of time, what will happen? It will finally create a huge amount of thermal load on that, and finally it can go bad. Okay, so that is the reason. So you should avoid that. So what we can do, let us say you are just switching on and off your switch. So instead of you switch on, motor starts moving. By the time it picks up, you switch it off. Okay, so by doing a high frequency switching on and off, you can limit the amount of power that goes into the system. Finally, it will, if power input to the system is low, so in that case what will happen? It will create, so you know, power is equal to torque into omega. So torque is constant over here because voltage is constant current that will flow, that will effectively change the speed of your motor. Okay, so this is how current, that is the effective voltage that is across the terminal is changed. So how does it look like? A PWM waveform looks like this. So you have a on time, your waveform is like this. You have a on time, it is on for a particular duration, and then it goes back to 0 and this. So it remains off. Again it is on. So it keeps on doing so. So for a particular cycle, this is the on time, this is the off time. So what will happen? So total on time by total time which is here, so that is the duty cycle of the PWM waveform. So PWM waveform is on time by total time, and it is expressed as percentage. So you just multiply it with 100, and that is percentage duty cycle. So percentage is from 0 to 100%. If I say 0% on time, that means it is off forever, and then in that case motor will stop. If it is 50% duty cycle, that means 50% of the time it is on and 50% of the time it is off. Got it? So that is how it is done. So this is known as a PWM waveform or pulse width modulation. This is used to control the effective power that goes into your motor, and that can finally control the speed. And how that is done? So you have, you already know you have a switch over here, you have a switch over here. So whatever direction is your motor is rotating, so you can have a transistor switch we can feed in with this much of this type of control signal to it. So that will continuously switch on and off whole of the H bridge. So motor as a whole can be switched on and off using this enabling switch. So PWM switches on and off this particular S enable switch. Okay, the switch which is here. So that is the way you can control the speed. So now you are ready with the system of H bridge with which you can go velocity that can vary from 0 to maximum on one direction to 0 to maximum on other direction, right? So if this is the velocity that is 0 to maximum on one direction to 0 to maximum on other directions. Got it? So this is how you can control the speed, direction, right? So in order to control the current, maybe you can have a DC chopper drive which can control the current, that effectively can control the current flowing through the armature coil, and finally the torque can be controlled. That is altogether a different story over here. So yes, controlling the angle needs a position feedback with a controller. So you need to have a servo mechanism over here. Servo means a feedback. We'll talk about that later on. But yes, using this, at least you can now, you are ready to control the direction. You are ready to control the velocity, direction, velocity. If you can control the current, you can also control the torque. What is remaining here is just controlling the position that needs a feedback device. Okay. So now braking. How can you achieve braking using such system? Now can you imagine if you can close this switch and this switch, close and keep this to open. So what will happen? If the motor is continuously running, it behaves like a generator. If you don't provide power to it by switching off these two switches S1 and S3, so it is not provided with current. So what it is now? It is already running. And what you have done here by closing these two switches S2 and S4 is you have short circuited this running generator. So you will have a huge amount of loop current that will flow through it, right? And that will create a back EMF and the reverse torque. That EMF is now short circuited and finally it creates a reverse torque which has a tendency to stop this motor. But it cannot bring it to zero, because when it comes closer to zero, hardly any EMF is generated and it is not sorted. So finally it cannot bring it to the zero situation. But yes, it can bring very close to the stopping speed of the motor when you can physically apply the brake, right? So, and more so, let us say if you can use this motor to generate electricity when you are not supplying it with power, right? By opening this too, you can have a battery which is here, which can be charged by having motor running in idle condition. Let's say your robot is going downward on a slope. Now you can use that power. You are not supplying it with the power. You rather, that motor has become, your wheel motor has become a generator. Now it is like a charger for this motor. So where it can charge the battery, right? So that is what is known as a regenerative type of drivers that is there. So yes, very commonly used type of driver is this, which probably you have used it in your hobby electronics and those kind of stuff during your school days or maybe in your intermediate. So this type of drivers are commonly here. So you see it has 1, 2, 3, 4. These 4 make up a H bridge over here. It has another H bridge which is here. So 2 sets of H bridge is clearly visible, and it can run first motor from here, second motor from here. This is an direction control bit where you can supply power comes in from here, power comes from here. So one of them may be supplying to control the velocity, other one for the direction. Again for velocity and direction for the first motor and for the second motor. For both the motors, velocity and direction wave can be given from here, power is inputted from here, and this is there. So this is a commonly used H-bridge driver, quite good for small robots, but not definitely suited for a big robot like industrial robot or like that, okay, which are required to have other compliances as well, right? So let us now have a demonstration of DC motor driving using industrial hardware. Okay, so now look closely the parameters, what this driver can do. This has an inbuilt DC motor driver, not like this one. This is also a driver. So this is an industrial driver where you have, see, this also can run first motor from here, second motor from here. That has to be powered from here. It can drive a 24 volt 1 amp motor, right? And input power to this can be given from here, that is 0, and the power is given here, and there are 2 inputs which are also there, okay. So yes, now you look closely, it can have speed control up to 16 bit. What does it mean actually? 0 to 100% of PWM cycle, this duty cycle can have a resolution of 16 bit, 2 to the power 16. That means so precisely you can increase the speed. So this is there, and then it has some electrical isolation, as because it is an industrial driver, it has to have this sort of safety inbuilt. So that is there. Okay, so you see this PWM clock frequency is very high, it is 32 kilohertz. So you can imagine you won't feel the switching on and off of your PWM cycle, right? If you switch on and off at a very small frequency, you will see a hum in your motor, that noise will come. So with such a high frequency, there is no noise, with such a good precision. So this is what is an industrial DC motor motion interface. It is known as a motion interface. Communication protocol to handle this is that I have used over here is to drive this kind of driver is EtherCAT, right? EtherCAT, not 3.0. That is the communication interface. So soft real time that I have used, that is TwinCAT 3.0 interface. On a standard PC I have used. So TwinCAT is a proprietary software layer over a standard Windows PC that allows you to do some real-time communication. That is a software layer, okay, that can do EtherCAT communication to its own drivers, to couplers, okay. With the couplers I can communicate using TwinCAT ADS using EtherCAT, okay. So it just requires a standard Ethernet card of 1 gigahertz or so, okay. So that is required for it to be implemented to do some real kind communication. So what I have used here for programming, I have used TwinCAT automation device specification ADS, TwinCAT ADS library I have used. That is the library that you can import to the Python environment, which allows you to access the motor runtime variable. Once you have declared those variables in TwinCAT, okay, so and made it available as an environment to the external TwinCAT ADS driver. So this driver can take that variable directly from the memory and do read and write operation to that memory location. Okay, so your Python code now can read write to the TwinCAT interface. TwinCAT finally sends it in real time to the external driver. I'll show you how it is all connected now. So this is the system. This is the system. So now this is the power supply. Power supply is for everything. It is for the motor driver also. Okay, it is 7332. That is the same one that is you saw just now. So this is the motor driver. This takes in power from your surge filter, which is here. Surge filters to avoid any kind of jitter, electrical noise from the main power supply, right? So that is there. This also supplies current to the Beckhoff couplers. Okay, so this is the Beckhoff coupler. Okay, so yes, that this coupler takes in data from your industrial PC, which is here, and PC has got the Python program with TwinCAT running. Okay, so it has a TwinCAT, that is the application layer over Windows IoT version that I had. Okay, it can also be installed on Windows CE. So finally this is the communication, that is the EtherCAT communication that is provided to that is coming to this device, which is the coupler. This finally transfers this to the through EtherCAT bus, which is here, that is provided to the driver, and driver finally takes in the data variables, process variables to the motor. So this is the driver. Okay, so hope you got this system, right? So you have a program. Let me just repeat, you have a program. Okay, you also have a software layer, that is the TwinCAT, where you will define all the process variable. TwinCAT is a real-time IO system, that can communicate with these external devices, whatever devices which are there. Okay, so it can talk to that, it can take in data, it can feed in data, right? And finally it can make variables accessible to the other programming environment. So over here this programming environment is Python, so that is what is changing the process variable. Okay, so now go to the actual system, how does it look like? So this is your industrial PC, this is your industrial PC, this is the UPS, this is EtherCAT coupler with surge filter with input output cards and motor drivers. Here is my DC motor that I am using today. Okay, so this is the DC motor. Forget about the other motors, I am not using this. Okay, so this is how. So hardware is rigged up like this. So finally let me just show you how the settings are done. So you just have to open the TwinCAT project in the TwinCAT environment, okay, new environment, and then choose the target. You just have to create the target over here. Okay, you can choose the target from here. Let me just see if I can show you somewhere from here. So now let me just capture this one. So here is your system, here is your system. You see how does it look like, how does it look like. So this is your environment, right? So you can now, this is the choosing the target, you are choosing the target now. Okay, this is, it is detecting your external IPC which is there. So IPC has got different IOs which are connected. So it has different terminals which are here, right? It has different terminals. You see input, you have terminals, you have motor drivers, you have other terminals, right? Other motor drivers which are, so everything can be seen which is here. Okay. So now let me just take it to little below. Now I'll set the process variable, create a PLC object. So once you have this terminal which is detected here, okay, now you can define the, so you select the target system here, you select the target system here, and then you scan for all the boxes which are attached to that CPU. This industrial PC is integrated with different IO boxes. One of them is your motor. So those boxes will have an object. If it is a DC motor, it has a DC motor object with different process variables. Okay, so I have just access to this PLC object. Okay, this object is selected. This object has got access reference, that is one of them is velocity, right? So that can be accessed. So this object has a process variable that is a velocity. Okay, that is to be accessed from your environment. So here you see, so this is having, this object has got multiple process variables. So you have enabling, you have reset, you have torque, right? You have velocity also, reduce the torque, true and false. So you see, this is the actual variable that I have to modify. This is my complete DC motor object. So it has all sorts of different process variables. Okay, so once I define this process variable, okay, so yes, now this is accessible to different external programming environment. Now let me just run this video and show you much clearly. Okay, okay. So this is just an example. When I'll show you very much in detail over here. So what you see here is, it is defining a PyADS. PyADS is the TwinCAT library, okay, that is imported here in the environment. Okay, that is imported here, and then PyADS is now able to connect to the external IP address, that is to the port, through a port, TCP port that is there. So that is connected. So you have created an object over here. After, once it is connected, object is created by the name PLC. Now that object is open. Once it is open, you can write to a PLC variable 0, 1, whatever is the value you can write. So one of the variable is enabling. So once I write it 1, that means that motor is enabled. So that means that motor is enabled. Now you can change the process variable of that motor, and that is known as a velocity. Now velocity is changed by changing the value. So very simple code it is just in Python. So now let me run. Yes, you see now what I am doing. Yes, so I am just changing the process variable over here. So you see what will happen. Let me just go back to this. So now when this was 0, you see your velocity, the process variable is 0 over here, velocity is 0. Once I change it, make it 5000 and I run this, it immediately changes the velocity variable to 5000, and that goes to the motor which is connected to the external driver. Okay, so that gives you some value of velocity. Now I have made it 10,000, motor runs at a higher speed, you can see. Again I have made it 15,000, it runs at even higher speed. So yes, now I will make it 0 again. Okay, the motor immediately stops. Now I will try to feed some negative value. Let me feed it minus 5000. Velocity, it runs with a slower speed, right? Make it at minus 10,000. It has picked up speed in a reverse direction with little more value. Minus 15,000. It goes at a little higher velocity again. Okay, so this is how you can go from maximum velocity in one direction to maximum velocity in the other direction. You can stop the motor also. That is what. Yes, so this was the video demonstration. With this, I'll stop here and hope you have learnt DC motor, how it is constructed, what is the principle behind, how a DC motor can be made to run using H-bridge driver. You have learnt about industrial system, how it can be rigged up, using a standard EtherCAT system. No worries, if you have a Modbus interface system, you can also access the process variable, right? And you are required to have Modbus IO interface that can be connected through Ethernet to your PC, right? And then you can access the Modbus variable, and Modbus interface card will have a motor driver card. You can have a IO card that is controlling the relays, which is finally controlling the motor. So all the process variables now is accessible using Modbus. So you can have various other interfaces too, not just Beckhoff TwinCAT based system, which is really very expensive. I would suggest you can start with Modbus based system, Modbus IO card and motor driver card if it is possible. Otherwise you can have a standard IO card, you can run a standard H-bridge and you can make your motor run. Okay. So that's all. In next class I'll be talking about stepper motor. What are stepper motors? Stepper motors, so hope if you remember your printer, faxes, try to get all these pictures that you can see, all the motors which are there, somewhere you must have seen it, right? So try to bring up your memories, and we'll talk about this later in the next class. That's all. Thanks a lot.